All right, cool. So at least my rough plan was that we'd be done probably by today and then turn in this first case problem on Wednesday. We're not done, but we're working hard. So we'll just extend the deadline, and that's fine. That happens all the time. We'll say next Monday. I think we'll be done by then, because we've done like 2/3 of the math. Last part is sort of wrapping up, figuring out what we want to say, and like making sense of of all the work that got put together. Plan? How's that? I'm just pausing for a second for logistic updates. It's just sunk in. All right. Yeah. There is a rubric. Let's see if this one pulls up. There we go. So you can take a look at the rubric that I have in there. For the most part, like 100% means there's no notes, like just nice job, you did everything that could have been done, and then kind of going down from there, like 10, 90, 80, 70, 50% is usually like something's wrong with the assignment. Either you're missing things or uploaded the wrong thing, and yeah, so based on this, usually, so the TA will try to give like some feedback, some specific feedback on your work, and then assign like kind of one of these bins of grades. Yeah, like we've been doing a lot of and so far we've done like a lot of math in class. Like how do we started off with like broad, what kind of problem is this? Got into a very specific, like, okay, it's this problem, let me do math. And the last part will be broadening out of like, why is that math important? Like, what is this telling you? And so the intro and the final part is up to you, like how you interpret that and how it's helpful. And then even the math, like if you have different initial thoughts on it, maybe you want to change how you approach it a little bit. Yeah, and it's a design problem, so it's rare that you and someone else see the design the same way. So if the TA is kind of thinking of it in a different way and you approached it differently than what they expected, then maybe you can revise it to kind of match expectations. I know that's a broad, like general, like truism of life. If you don't do what people expected, you have to change and do what they expected. But that's kind of what we're going for. And it's a general sort of engineering approach of like someone says, hey, I need a swing set, but I want it to swing right here where a tree is. Have you ever seen that diagram of like what the client wanted, what the engineer designed? No? Maybe? Facebook, like the source of all great communication, but it's kind of like what marketing said you need, like a swing set with three things. What sales ordered a swing set with like extra lines attached to it. engineer designed it. It's still a swing, but it's not actually ever gonna swing. The crew modified it. They like cut the tree down, put the tree back up on stilts. Meanwhile, all the customer wanted was like a tire with a rope on it. So as long as you're like talking through, like if you're making your process clear and addressing things, then you'll get to the right kind of bottom right solution. Sometimes it's more work, sometimes less work, but I like the manufactured one. Like, it's definitely swingable, but it's like right into the tree, like the least. Last time on Applied Mechanics 2, this was before Patriots had a rough game last night. It was like watching the unstoppable force meet the immovable object, right? It just, nobody was doing anything, just slowly getting field goals, and then finally like excitement at the last like 2 minutes. Like, where was that? But I think everybody was just tired and the game was already over. But anyway, now we're here. Game's over. Football season's over. On to the next thing. Next up is March Madness, right? Get UConn up in there. So last time, we kind of got to this point where some people recognize this, like when you plug in an e to the st into that differential equation, it looks like a Laplace transform. That's because it is. Like, it is a Laplace transform. The only difference is we didn't do like infinite integrals to prove that that's true. It's loud today. I like the excitement. Is it all connected to this class, or is it something else? You, what are you talking about? White hoodie, what are you talking about? The dorm room flooded? Oh man, that has nothing to do with this, but that's terrible. I mean, flooding, I guess it's a little bit of dynamics. It's mostly like Bernoulli equation, right? I guess there's some dynamics, but yeah. Oh man, your dorm or someone else's? Oh, that sucks. Sorry to hear that. Yeah, I was wondering, like, are other people also flooded? I was wondering, like, what's going on today? Or just something else. And I called you out but I just wanted to know, like, what's going on? Do we need something else for today? Are we doing something else? It's okay. Part of, did I already say this? The yoga practice, recognizing where you're at, where your body's at. Mostly mind here. Okay. Where are we at? Are we in like an engineering state, or are we like in fight or flight stage of, man, what am I gonna do with this flooded dorm room? We can be anywhere. You can be anywhere you want. Well, not anywhere you want. Like, the universe has put you there, and you have to deal. Oh, now it's quiet because I called someone out. No one likes being called out. Sorry. Thank you for sharing. Yeah, I did like random call outs one time. Like, I had an actual like randomizer that I wrote in Python. Oh my God, people were so scared. Like, I think people dropped the course because they're like, oh my God, what if he randomly calls on me? It's like, it's fine. It's not that big a deal. Yeah, it's fine. Okay, so we left off with, we had like two constants, same thing that happened with sines and cosines. Here we have exponential kind of things. And we need to figure out what is A, what is B with those two because we know initial position, initial velocity, initial value problem. We know the form. What is A? What is B? So what do we think? What is this? What is that? Take a second, think about it, or try it. Better to try it, like calculate it. Thanks. Oh, Peter. Good, thanks. No blue? Okay. So that's even 0. Every force is either a position or a velocity. A plus B. We have x of t which gets me nowhere. That gets me to A equals negative. That's really what it is, bro. I think for the next one, if there's concerts, we should get first
But that's like before t equals 0.
No, it's all the time, right? It should be all the time.
Oh, so yeah.
Otherwise,
When t equals something else, it would be equal to 0.
all right. So one thing that we came up with, at least as I was walking around, was like A is negative B. Yeah. Okay. And then A plus MGB no T. Trying to take a derivative there, right? And then there's some constant like A that is that 3.1 minus mg over b, where those are like, what do we think? Agree, disagree? Yeah. Where did it go? Yeah. Oh, yeah, when we do a derivative, I guess we do need that negative. All right. So this would be so you mean the negative b over m? Like that one should pop out when we take a derivative? I think you're right. The b is gone, so plus a 0. And then this t disappears. Bless you. Kind of like that. Do we end up with a m squared and b squared? Kept it factored? Oh, okay. Something. Yeah, multiply both sides by m over b. Then we just have a, something like this. Seems like we got some progress. Then, like, taking all that and kind of plugging it back in. A is some value, because we have like 3 minus mass divided by b times mass over b. Then plugging those in. How are we doing? Yeah. Oh, when I'm solving for that velocity? Yeah, e to the 0. Sorry, I was answering a different question. Like, oh, yeah, I forgot the b over m. Yeah, but when e to the 0, it all cancels out to 1. Yeah, so if we had like e to the negative b over m times 0 up here. Kind of like this. Not bad. Good start to the day. Got like an equation. And just kind of taking stock of like constants, what do we know, what's going on. This was like a V0 value that we can solve for, like either with a kinematic equation of like how fast it's moving if it's dropped from rest for after half a meter. G is a known, mass is a given, kind of 0.1 kilograms. B is a known 5 kilogram per second. Like viscous damping. So we know, like we can plug in all those values and kind of get to what's going on. What is this function going to look like? I know some people had drawn like an initial guess of like what was going to happen for these different things. What does this function look like? I saw it's something like this. Like that.
Seems because with that graphic representation, the like x over time.
Yeah, x over, is this x of t? Is that x of t? All right, take a second. Definitely, you can talk to each other. Like this is not a quiz or a closed book sort of thing. What is this thing? What's happening? Like, what did we just figure out with these like constants and functions? What's going on here? What is this thing doing? Do we still think decays to constant value? What was x at 0 in our graph? In our, like our very first. It's got to be 0. So it's probably not going to start tall, right? It's got to start down here. The slope has got to be 3. Like it has to have a slope of v0, because we said don't make this function unless it's a slope of v0. Like we did that. We're like, you behave yourself, be slope 3 at this time, and then solve for everything from there. So there's like, at least like one part we kind of know, like, again, the initial value, what it looks like for that first little snippet of time. So do we think we'll kind of go up and then go somewhere? It's probably not going to go down, right? Like the fluid's not going to drive it up and away from the fluid. It's not that it can't. In our model, there's no, once it touches the fluid, there's no, same as the spring. Like as soon as it touches the spring, it can do anything as long as it's still connected to the spring for our model, for our free body diagram. You could change that. You can kind of make different versions of it, but first approximation. So probably it'll keep going into the fluid because the fluid's not going to push it back into negative. What is, so not infinity, like I'm not trying to take a limit here, but what happens when t is big? A big number can mean different things depending on, really only depending on one thing, but we can get to that. So as t gets big, what does this thing look like? Yep. There's 2, but yeah, go for it and then we'll follow up. Approaches a limit, okay.
It's going to start to look like a linear equation because the e to negative v over mc is going to approach 0.
Okay.
That a is going to be, that sum of the a is just going to be negative a. Mg over b is the constant value.
Yeah, just kind of some slope, right? So if we say A is down here, really we should kind of go to that line, right? That should be our asymptote, like something like that. I mean, we can always just like plot it, right? Like we have all the numbers, we can plot it and just say like, oh, look at that. I was just trying to get you to like think about, is this what we wanted? Is this describing, did we get a function that actually solves for like damped motion? Dropping it in, hits the fluid, and then at some point it's got a constant velocity. Is that what? Maybe? It's at least what I told you to do, right? Do this. Here's damping, there's gravity, and then solve it this way. Some people had the idea of like, hey, what if there was buoyancy in here? How would that change this problem? What would buoyancy force do to, yeah?
Potentially bring the object back towards the surface
back towards the surface.
Instead of flattening out horizontally, it would eventually, X would start decreasing back to 0 as it floats to the surface.
As it floats to the surface. Yeah, it depends on like how buoyant. But what is buoyancy force? Like, what is that force? Does it depend on depth? Chemistry will say yes, because depth changes pressure, pressure changes density. It's not, we're not dealing with changing density, water, or whatever the fluid is. We're not dealing with changing density. What is buoyancy? Yeah.
It's the weight of the displaced water.
Yeah, so whatever fluid you displace, it's that weight is applied. Oh, am I going the wrong way? So the buoyancy just decreases how much gravity there is. How does that sound? Neutral buoyancy would mean there is no gravity, like as soon as you hit it, there is no gravity. If buoyancy is equal to 2 times the weight of the object, then this thing's gonna have some kind of extra term where it goes down and then comes back up. And then whatever we want to do with that information as it gets back to like 0. Is it constant then, or? Do we want to see what it looks like? Try plotting it? Or no? Yep. Okay, let's try it. And what is this? 3.1 minus m times g over b. And m over b times that. How's that look? Weird, right? But it does something. Like initially it was moving real fast, but it hit the fluid, slows down by a lot, and then, oh, it's weird that it bounces it up. That can't be right. Why would it bounce it out? I think I did something wrong. Yeah. You got the reverse? Up then down? Oh, A is a negative thing here, right? Like that. That looks better. At least to me, that looks better. What do you think? What did I do wrong the first time? Did you see that? I had a negative sign for, I was missing that negative sign on the A equals, and it ended up flipping that exponential sort of thing. So now, to me, it kind of makes sense. It's moving real fast, slows down, and then by the end it's just moving constant speed. So here, at least to me, time is big. Like, I don't need to go to time infinity to say that it's constant speed. Even half a second, it's definitely, I know it's an asymptote, so technically it's not really constant speed, but for all engineering purposes, it's already gone through like 5 time constants of motion, so it's back to the steady state sort of constant speed problem. All right. We've done this twice now, figuring out free body diagrams. We kind of know at least 2 different types of motion. Like, it could be bouncing, like oscillating, or it could be damped in a different way. What about for this friction case where we have friction? Do you already have free body diagram for this one? I know we drew some stuff, but do you want to revisit, double check before you jump into like differential equations? All right, check in. What did you think it was? What do you want to change? What kind of motion are you expecting out of this? So what's happening? And then because we're going to do some differential equations, I'm going to say this one is positive x. I'm just prescribing like, hey, this is my coordinate system. Down is positive, to the right is positive. So we're not going to move left, right, we're only going to move up, down. Mostly down, but. Again, this is where like comparing ideas helps. What do we think about this? Left side, right side, normal force. What do we know about left and right normal forces? You can't trust them, that's the main thing. No, they're fine. They're cool. Do we know anything about those? Like, why did I write NL and NR? So one, they're called normal not because like they act normally, but because they're 90 degrees. Normal. I don't know what normal means. So many different things in so many different contexts. Like socially normal is not me. Then there's like statistically normal, which describes like a whole distribution of things. Now normal is also 90 degrees. Anyway, so this is the 90-degree normal, not the statistically or socially normal. So normal to our path. So it does cause acceleration, but if it's normal to the path, it can't do work on the system. So it's not going to change like kinetic energy or something. Okay. Can the left side be bigger than the right side? No? Based off friction. Oh, based off friction. Okay.
Depends on like the jaggedness of the wall.
Depends on the wall.
Yeah, the wall
Okay.
is the parallel. Like it's like,
Okay. So it depends.
yeah.
It's good to hedge bets. Like it depends. Hedge your bets.
Like
Yeah.
alternating strength as the wind goes down.
Okay. Yeah. Like if it's actually macroscopically jostling. Usually rough sides are kind of microscopic. It would be kind of cool to have like a kid's toy, like shuffle it back and forth. Okay, not maybe we know, maybe we don't know. It depends. It sounds like. What about friction? Would we write for that one? Because I saw more than one friction answer. Yep.
Two forces from the left and right going up.
Force of friction, left and right. Friction left, friction right. If MA is down, so if I'm saying MA has to be down, now do I know anything about my left and right normal forces? Yeah. So if we're saying the thing's moving left and right, then we need a force to move it left and right. Like there's got to be a cause for the motion. But if we're saying it's going straight down, equally we have to say there's a cause for that, and it's that whatever forces are on the left side, there's equal opposite on the right side. So depending on how you want to approach an engineering problem, if you want to say that, yeah, there's a lot of motion going on, or if you want to say it's going straight down and just trying to figure out how it's falling. Oh, we're almost out of time. Okay. At least from what I have so far, MA is mg minus 2 mu n. It's a good start. Then we'll pick it up from there on Wednesday.